Right now, in your pocket, one piece of mathematics is running billions of times every second. It untangles your music, keeps your Wi-Fi alive, shrinks your photos, and turns raw scanner data into images of your brain. This is the story of the Fourier transform and the algorithm that made it fast. Think about what your phone did in the last second. It held a Wi-Fi link steady through 2 walls. It streamed music that was compressed 10 times smaller. Maybe it sharpened a photo. Underneath every one of those jobs is the same mathematical move. Take a messy signal and split it into the pure frequencies it is made of. The only reason this works in real time is one algorithm, the fast Fourier transform. To see why it matters, we need to start with what a signal actually is. A signal is just a measurement that changes over time. Speak into a microphone, and air pressure wiggles a membrane, tracing a continuous curve. A computer cannot store a continuous curve, so it samples it. It reads the height of that curve over and over, thousands of times per second, and keeps only the numbers. CD audio takes 44,100 samples every second. From here on, a signal is simply a long list of numbers. Here is the problem. In time, a real signal looks like chaos. The wiggly mess on the left is actually just 3 pure tones added together, but staring at the waveform tells you almost nothing. There is a second way to look at it. Instead of asking what the value is at each moment, ask how much of each frequency is inside. In that view, the same signal becomes 3 clean spikes. Same information, 2 portraits. The Fourier transform is the bridge between them. So what exactly is a pure tone? Take a point moving around a circle at a steady speed and track only its height. You get a sine wave. The number of full turns per second is the frequency, measured in hertz. The size of the circle is the amplitude. And where the point starts on the circle is the phase. Keep this spinning circle in mind. It is about to do all the heavy lifting. Now, how do you check how much 3 Hz is hiding inside a messy signal? Multiply the signal by a probe, a pure 3 Hz wave, point by point, and average the result. If the signal contains 3 Hz, the 2 waves rise and fall together. The product stays mostly positive, and the average comes out large. If it does not, positive and negative patches cancel, and the average lands near 0. Watch the meter as the probe sweeps. That single move, multiply then average, is the entire Fourier transform. Everything else is bookkeeping. There is an even more beautiful way to see it. Wind the signal around a circle, like thread on a spool, at some chosen speed. For most winding speeds, the heavy and light parts spread out evenly, so the center of mass of the wound curve stays near the middle. But when the winding speed matches a frequency hiding in the signal, all the peaks pile up on one side, and the center of mass lurches outward. Track that lurch across every winding speed, and you are literally drawing the spectrum. Let's make it precise. Euler's formula says e to the I theta is a point on a circle at angle theta, a spinning arrow. The discrete Fourier transform takes your n samples, multiplies each one by an arrow spinning backwards at frequency k, and adds them all up. The sum is exactly that center of mass. One complex number, whose length says how strong frequency k is, and whose angle says where it starts. Compute it for every k, and you have the full spectrum. But count the work. Each of the n frequency bins needs a sum over all n samples. That is n squared multiplications. 1,000 samples, 1,000,000 operations. Fine. But 1 single second of CD audio is 44,000 samples, which is nearly 2 billion multiplications, for 1 second of sound. Through the 1950s, this was the wall. The transform worked, and it was too slow to use. The escape comes from a hidden symmetry. Those spinning arrows are not millions of different numbers. They are always one of just n points, spaced evenly around the unit circle, the roots of unity. The huge DFT matrix is stuffed with repeats, and the points come in mirror pairs. Each one is exactly minus the point across the circle. The same products are being computed over and over. All that work is redundant, if you can find a way to reorganize it. Here is the reorganization. Split the samples by position. Evens in one pile, odds in the other. Each pile gets its own half-size transform, E and O. Then the algebra collapses into one line. Bin k of the full transform is E of k, plus a twiddle factor times O of k. And thanks to the mirror symmetry, bin k plus n over 2 is the same two numbers, with a minus sign. Two half-size transforms replace one big one, and you have already saved almost half the work from a single split. Now do not stop. Each half splits again and again until you are down to single samples, whose transform is just themselves. The whole computation becomes log m stages, and each stage is only n simple operations, drawn as crossing pairs that engineers call butterflies. Total cost, m log n. This is the fast Fourier transform, not a new transform, the exact same answer, computed without repeating a single piece of work. Feel the difference. 1 million points costs a trillion operations the direct way, and about 20 million with the FFT, 50,000 times less. On 1960s hardware, that was the gap between 12 days of computing and 20 seconds. Watch the race. The FFT is done while the direct method has barely left the start line. The strange part is the history. Gauss had the trick in 1805, scribbled in his notes while tracking asteroids, and he never published it. It was rediscovered in 1965 by James Cooley and John Tukey. And Tukey's motivation was deadly serious, detecting Soviet nuclear tests from seismometer recordings, which demanded fast spectral analysis. Their 5-page paper exploded across every field at once. It is still called the most important numerical algorithm of our lifetime. Once spectra became cheap, whole technologies followed. Filtering, convolution, which costs m squared head-on, becomes simple multiplication in the frequency domain. Your Wi-Fi and 5G signals are literally built with an inverse FFT, packing data onto hundreds of subcarriers at once. JPEG and MP3 run a Fourier cousin, the discrete cosine transform, and quietly delete the frequencies your eyes and ears cannot perceive. And an MRI machine measures the spatial frequencies of your body, then runs an inverse transform to turn them into a picture. Different machines, same engine. One honest caveat before we close. Frequency resolution costs time. A short window of signal can only resolve coarse frequency detail, and a long window blurs the timing. That trade-off is the uncertainty principle of signal processing. Real systems slice the signal into windows and accept the blur. That is the spectrogram. And research keeps pushing. Wavelets adapt the window to the scale, and sparse FFTs go even faster when only a few frequencies matter. From a spinning circle, to multiply then average, to a recursion that collapsed m squared into n log n. The next time music streams, or a scan resolves, you will know the machinery underneath. One idea, computing the hidden spectrum of everything.